Okay, we are now recording and streaming. So welcome everyone. We have more than 30 people today on our Warsaw University Astronomical Observatory Tuesday seminars at 4 p.m. Today our guest is Professor Michał Bejger from CAMK, from Nicolaus Copernicus Center in Warsaw of the Polish Academy of Sciences. He is a member of LIGO, Virgo, and Polgraph collaborations and is very active in the field of gravitational waves. And he's going to tell us about enhancing gravitational wave science with machine learning. Michał, please.
Hello, everybody. And so it's a great pleasure to speak at the Astronomical Observatory seminar in Warsaw. I'm a graduate from this observatory, so this is I treat it as one of my homes. This seminar is also a little bit kind of to me some sort of a kind of a walk along the history lane, or kind of a memory lane, because I will be talking about automatizing data analysis and automatization and algorithmic methods in data analysis mostly here, which is very similar to what I was doing as my first scientific work under the supervision of Professor Bogdan Płaczyński with CAMK Mizerski a couple of years ago. So this is a little bit of a loop for me with a little bit of twist because of gravitational waves. So let me move to my topic. So I want to talk about gravitational waves, but from the point of view of how this new type of information can be treated with machine learning. So as you all know, we recently had a second catalog of gravitational wave transient events published, and in comparison to electromagnetic observation of black holes, now we have more and more new measurements of black hole masses. So this how it looked like after the 01 and 02 LIGO Virgo runs. We had in total 10 black hole systems detected in one neutron star system. And then this GWTC2 catalog provided an addition of 40 new measurements. So now we have much more measurements, actually, which is kind of funny, than this measured black holes that are measured with usual methods. Probably Łukasz can correct me because of the microlensing measurements that are not here, but they maybe should be. But this progress in this last 5 years is quite astonishing, at least to me, and we expect much more measurement and much more different signals in the near future, because there will be new runs incoming. In a year there will be 04 run with even a larger sensitivity, so larger volume of space available to detectors. By the way, if you would like to interrupt me, please do, or write your questions in the chat. But I prefer rather if you just ask me on the microphone whenever you want. Okay, so the state of the art now is that we have working detectors, 3 detectors, LIGO and Virgo, that are becoming more and more sensitive, so reaching farther and farther in space, larger and larger volume, and more detections will be coming. And this, of course, is a quite unusual, because we were starved with data for a long time. Now we have somehow, maybe one can think that we have too much of data, and we have to somehow deal with it. So this is the first motivation to use some kind of algorithmic, automatized, fast methods to treat the data, or in other words, to reduce the data in such a way that we only can fish out this interesting astrophysical signals. So in numbers, it looks like that we had this 01 run, 3 detectors. In 02, we had in addition 8. Then at the end of O2, Virgo joined, and actually at this moment when Virgo detector joined LIGO, the number of detections started to grow more rapidly, which is a coincidence, but I think they were just more sensitive at that time, and the growth is more or less stable in O3 and like that. And so this picture shows the public alerts. And the GWTC2 catalog provided only these detections from this first part of O3. So we still are analyzing the O3b part. Just to give you a little bit of kind of like a teaser, what can happen is that we have provided 23 GCN public alerts. It should be 23, not 26 here, I think. And then there were 13 new events found offline. So they were not announced as public events in the online mode, but they were found later. So we kind of expect a similar number of, or maybe more number of new events not announced previously as a public alert in O3b. So this number will be more or less like maybe 80 or something like that at the end of the O3. So this is already quite a nice number of detections. Yes, and so let's move on. Another thing is that the detectors are becoming more and more stable. So we have now 3 working detectors, and actually maybe 4 detectors because CAGRA is joining. Actually, well, it has joined, but with a quite poor sensitivity at the moment. But in O4, it hopefully will be really useful. And the detectors are working in this kind of observation mode, that they are on as long as possible, which is more or less like 70% of the time. And the more detectors observing at the same time, the better, of course, right? But here you can see that we had 3 detectors, triple interferometer, working as a network, 2 LIGO detectors and 1 Virgo, in let's say 45% of the time, double interferometers in let's say almost 40, and single interferometer in 15% of the time, because there were all kinds of problems happening. You know, some of them are being switched off, and earthquakes and other things. So, and this slide is to kind of to show you how this kind of works. The more the more detectors, the better, because then we detect the same wave in many detectors. We have more confidence in detection. But on the other hand, we have 15% of time when there is only 1 detector working, and then we cannot use this coincidence method to actually establish significance for a detector for the detection. So we can miss actually a few events because of this single interferometer time. So this is another motivation to look closely at the methods of data analysis that can be used, maybe automatized, with a single detection, single detector data to improve this, perhaps. So I will just flash this slide with the sensitivity curve of the detector. The sensitivity is expressed by the so-called amplitude spectral density, which is something like a Fourier transform. It is written here. This explains this weird unit, and amplitude over the square root of hertz. Basically, the lower this line is, because the detector is a noise-dominated detector, the more sensitivity is. So this line is being evaluated from the very noisy data, and all these peaks here, these lines and weird features are actually instrumental, more or less stationary instrumental features. Some of them are put here because they are for calibration, because as you know, the interferometer is composed of mirrors. The mirrors are hanging on specific suspensions, and the suspensions have to be calibrated. They have some characteristic frequencies, and the frequencies correspond to specific lines here. Sorry, I talk too much. I think something wrong with my throat. And the other features here are, for example, related to the electric frequency in US, because this is LIGO, so we should expect something at 60 hertz. And indeed, this is this huge spike. This is 60 hertz mains in US. So not very much related to anything, but just to give you a number, how much data the detector is producing per second is something like 50 megabytes, something like 50 or maybe slightly more per second. So this is the whole data that we are producing, the main data, this gravitational wave channel, but also a lot of auxiliary data that is used to veto spurious detections and and to calibrate the detector and do all kinds of things to understand better how it works. So second introductory slide about the data itself is that the data is, the raw data looks like that. It's a time series for 2 detectors. And it's very much dominated by low frequency. So these are seconds here. And this amplitude here is 10 to the minus 18. And you can see a lot of oscillations that are of the, let's say, of the order of, like, I don't know, 1/10 of a second or something like that. And they are related to seismic and anthropogenic disturbances, noise, and that produce a huge amplitude. So the gravitational wave, if it is there, in this particular case, it is. This is the GW150914 piece of data. It is very small, and here in this noisy low frequency data. So we can filter out this data, just remove this part of the data content, low frequency, for example. And if we do it, then we can reveal this actually very strong signal. This was quite a strong signal, so it can be for which we can do something like this, band pass it, and we see that there is something in addition, something much smaller, 10 to the minus. Unfortunately, it's not written here, but it's 10 to the minus 21. So this is 1,000 times smaller than this amplitude. So for strong signals, one can do it. One can just filter out some frequencies, whiten data. Whitening means that we take into account different sensitivities at different frequencies. So we somehow normalize the sensitivity by dividing by this amplitude spectral density, and so on. We have the signal like that, but it's not always the case. And also, there are all kinds of spurious signals that are happening all the time in the data that may look like that even. And then what to do with that? So this spurious signals are called glitches. So I'm showing you here some sort of a representation of the most notorious glitches that we observe in the LIGO detectors. Such a glitch zoo, this is a spectrogram. This is a time versus frequency representation. So in the spectrogram, one can, for example, recognize the chirp, this classical characteristic shape of the chirp signal that is produced by the binary system. The binary is getting close, the components are getting closer and closer to each other, radiating frequency, gravitational wave as gravitational waves at higher and higher frequencies. And so the signal is getting stronger and it's increasing in frequency. So we have this evolution of binary as a chirp plotted here. But the chirp is very similar to this guy that are called blips or blip glitches. And that can be very easily mistaken if you look at such a representation, or in general, they can be mistaken for weak chirps. And so there is like a lot of them, different ones. They come from different parts of the detector. Some of them are a complete mystery. Like, for example, those blips, we don't know how they are produced. They just happen from time to time. And this is a mystery, how they occur, but we have to somehow take them into account. So first first job for machine learning could be, for example, to catalog them, to try to detect them and recognize them and flag at least, flag and veto and remove if we could. So there are very nice programs to do it involving volunteer scientists like Gravity-SPY. Now there is a European version of it, Reinforce, that basically prepares such a training data for machine learning to recognize such glitches. Okay, so there is yet another thing that is related to the signals, because they don't have to be short, they don't have to be known. So from the point of view of astrophysics, they can come from binaries, they can come from explosions, they can come from deformed stars that are rotating stably like pulsars. And according to what is the source, we have to choose a method to detect them. Whether we know the signal, how it looks like, then we can use, for example, matched filtering. We can filter out the signal of a known waveform, or we can, for example, look for an excess power in the time series in the spectrogram. And then there is this huge field that basically correlates the data between many detectors. So there are many methods that can be used. Not all of them, not even one is good for everything. Some of them are good only for one type of source. Some of them are actually not very good for even one type of source, and so on. So there is like this is work in progress. People are trying to invent new ways of dealing with this very noisy data. That's the main problem, that the data is noisy and the signals are almost always hidden very deep in the noise. So I want to talk a little bit about matched filtering. So matched filtering means that we know the waveform, and so we can basically apply a filter and kind of filter it out. So the most simple filter that one can imagine is a Fourier transform, because the sinusoid is just a filter for the Fourier transform. So if you have a hidden signal in the time domain data, like here, this is actually a very strong signal. Then we can basically apply Fourier transform to this piece of data, and we will have a peak corresponding to the frequency of this sinusoid. So it's a kind of a simple demonstration that shows that we can find even very, very weak signals, very small amplitude, because the signal to noise calculated by this filter, by the Fourier transform, but by applying the Fourier transform to the long piece of data, basically grows with the square root of time. So we can really find very weak signals if we have enough data. More mathematically, this looks like that we have a model, we have a data, and we correlate the model with the data, and we normalize or kind of take into account different sensitivities at different frequencies by this power spectral density or amplitude spectral density. So this is our method of correlating signals with the data, and this will give us predicted signal to noise of this match between our model and the data. So in pictures, it looks like that we have some data, noisy data. We have a model. We multiply one by the other. We divide this product by the spectral density, and do the integration, in time, right? In the time that is interesting for us. And then if it matches, then we have a peak at specific point that, for example, corresponds to this maximum amplitude or some other chosen point. So it looks easy when I talk about it like that, but of course the problem is with this. We have to select the best matching filter, the best matching template, and this template is generated from astrophysics, because, for example, this is a binary black hole waveform. We have to pick the numbers that enter this waveform such that we cover the space of parameters sufficiently in a sufficiently dense way, so that we don't miss it. Because if we will not pick it carefully, then our template bank will be too sparse and we will not find it. And this is a problem, because we actually have many parameters to take into account in a binary system: masses, spins. We have, if these are not black holes, then or other exotic objects that can be tidally deformed, then we have tidal deformability. We have inclination of the system, and all these things like distance and polarization, sky localization, which is important because the detectors are not sensitive in the same way in different directions, and so on. So in total, there are like 10 plus or 15 plus parameters that have to be taken into account. And then when we have a template bank, we have to do for each of the templates this type of match filter, calculate the integral, and find the best one. So that was why this GW 150914 took something like 6 months to publish, and there were 250 mega CPU hours burned for checking and rechecking the best template. So because now it's probably much more optimized, but it was quite an effort to actually calculate this best filter. So astrophysically, we are interested in masses of the binary, which is the masses of binary are encoded at the basically Newtonian level as a chirp mass. And then at higher post-Newtonian orders, we have mass ratio or a total mass. Then we have spins at even higher orders. And then at a very high order, at 5 pn, we can hope for measuring, or at least constraining, tidal deformability, which is basically the mutual deformation of the components. So one can express this tidal deformability as this. So that tidal deformability of a component is this one, and then there is the same structure, but when one is inverted with 2, because it's a symmetric sum weighted by masses. And one can also think about tidal deformability as some sort of one can transform it into a proxy that I call it here a calligraphic R. It's like a radius. It has a dimension of a radius, so it's like a kind of a counterpart to this chirp mass. So that would be something like a chirp radius for a binary. So one can think about this also in these terms, like we are measuring some sense mass and something like a radius from the tidal deformability. And of course, then we can also measure distances and things like that. Okay, so that was quite a long introduction. Let me move on and talk about machine learning. So there are all kinds of ways the machine learning can be applied to the case when one has some data, right? So, and especially this problematic noisy data. The only thing that is actually good and nice about this data is that it is sampled with a uniform sampling, because it is not taken, for example, like by the telescope when the weather is good or not, but we have a sampling rate that is fixed, and we are taking the data that is very nice time series. But otherwise, it's horrible because it's noisy, and there are all kinds of features, non-stationarities and glitches there. So I will be mostly talking about detecting signals using machine learning, classifying different time series, because we can try to classify signals or detect signals in the data, or maybe glitches, or maybe nothing, something like noise. We are interested only in noise. So this can also be classified by machine learning methods, we can then go further and estimate the parameters of the signal that is hidden in the data. Or we can do something else. We can remove the noise and uncover the signal that is hidden in the noise. We can take the data that we have already, like for example, the masses and I don't know, other parameters of the binaries, and try to study the patterns that are there in this data. Maybe there is something that is non-uniform, for example, that would be a sign of some kind of an astrophysical process that is imprinted in this pattern. We can also forecast the waveforms that I will be talking at the end. And so then there are, of course, all kinds of additional things that can be done, like, for example, recommendation systems, whether do something or not based on the data, whether one should try something else, and so on. So this is a huge field. I will not talk about that, unfortunately, but it's nice. And then, of course, how to maintain the detectors. One can control the interferometric detectors using some algorithms that will optimize something in the laser systems, for example, and characterize the detectors. So identify the noise, remove them, or even maybe not only show correlation between channels, between these witness channels, these auxiliary channels that are just maintaining or studying the state of the detector and the main channel, but actually even show that there is some sort of causal connection between them. So the field is very broad, and at the end I will show you, I will give you the reference to the review paper that basically describes all this. I will just talk about these things. So, and I will be mostly talking about neural networks. So, this is, of course, impossible to really describe everything in detail with this whole technology that got invented in the last couple of years. All these tricks that were basically, they just appeared in some sense organically, because people were doing a lot of experiments and some things started to work, for example. So there is sometimes not a strict theory behind it, but things just work. So I will not go into that very much. Just show a couple of cases that are useful. So one of them is the convolutional neural network that you probably know. That is the one that can distinguish between cats and dogs. So if I show such a neural network that reads 2D data, the images, a picture of the dog, the network was trained on this data, it will be able to recognize that the picture is a picture of the dog, because it is composed of several layers. This is this hidden, deep part of the network that is here designed to be able to detect larger pieces of the image. So it starts with pixels, then it can interpret or detect edges, then it can sometimes it's done in a different way, but it can detect combination of edges. So it's already some features that are at the end important for the dog picture, and so on and so on. And by adjusting this whole structure, which is composed of individual neurons, and that are each of them has some specific degrees of freedom, like weights and biases. Basically, it's a huge nonlinear function that can be adjusted, fitted. One can, by training, change these values in such a way that it will be distinguishing one class from the other class. So it's nothing magical in the sense that these connections are some kind of deterministic way of transferring information from the input to the output, but because of the complexity of it, it's very nonlinear, and so then one basically loses a grip on what is actually going on in some sense. So one can have a look at this at these layers, and sometimes it's not very obvious what is going on. So in the sense, this is a black box. But otherwise, it's just linear algebra. Okay, so one can classify not only images, but like multi-dimensional images, multi-dimensional distributions. So this is a case that we have tried recently with my colleagues at Copernicus Center. We have an output from a gravitational wave search, and that outputs signal candidate distributions. These are not even signals, but some kind of distributions around the signal in a kind of a complicated and multidimensional way. This is a multidimensional distribution, but one can feed this to the neural network in a form of images or even 1D, somehow like time series, but they are not time series, they are distributions, and train the algorithm to recognize whether something is a signal by the shape of this complicated multidimensional structure, or that is a local artifact, local to the detector, so-called line, like those lines in the sensitivity curve, or that is nothing, like noise, for example. So this multidimensionality of the data is not a problem here, because for us, it looks like complete garbage, but for the neural network, it looks like something if we have enough data to train. So we have to have, first of all, a lot of data we can show to the network. So this is a case that is a simple case, just to classify things. Then we can try to detect things. So we can try to invent a model, neural network that could be a better algorithm, a kind of a substitute, an alternative to matched filtering itself, because matched filtering is a very established theory that has proofs and theorems, and the theorems say that this is an optimal method in Gaussian noise, non-stationary Gaussian noise. The matched filter is the best way to do, in the sense that you get the highest signal to noise. But we know that in our case, the noise is not Gaussian, non-stationary, and there is all kinds of problems there. So maybe we don't need this optimal method that is nevertheless very slow compared to the other methods. We maybe want to have something that is cheaper computationally, but works almost as good, or maybe as good. So this is a typical signal hidden in the data. So if I would not plot it, you would not see that there is something here hidden. Of a binary black hole signal of such masses. The signal to noise is not very high, not very low, but it's one of those that we usually detect. And one can construct a neural network so that it can recognize such time series without a signal, with the time series with the signal. And it works comparably as good as the matched filter method, and it's much faster. So of course, the question is, what was the data? Maybe the data was too nice. Maybe the network learned something else, and so on. So there's always this question about the training of the data. How the algorithm actually knows what to detect, and whether we can believe in confidently believe in this classification probability that it is outputting the output. So, and this is a valid question, because we don't have a theory behind this simple classifier that what it outputs is a credible interval or some kind of probability and so on. So it's still an open question, and we are trying to make a serious experiment with in this direction with colleagues from APC in Paris, with Agata Trovato and Marie Chasson-Motin, to to basically experiment on a simple classifier that is classifying noise signal. So this is a pure noise, realistic, but there is nothing else there, just the noise of the detector. This is noise plus injected signal because we can produce waveforms and add them to the data. And the third class is a glitch type. So there's some kind of a glitchy thing here. And we have the simple classifier, and we are studying this to come up with methods to produce a reliable I'm looking for a better word than reliable, because it may be maybe this is not the perfect description of what it can do. Actually, it's like a sufficiently good sieve to filter to sieve out the garbage, like the glitches and the noise, and only leave candidates for signals. Because I think we can never hope for really something that is like a much filter that has such a level of scrutiny in mathematical sense. But maybe we'll find something. Just moving on, this is our small network that is actually not very good, but this is just for testing. We are at this level not really trying to make it work the best. Of course, we have better ones. So we have this confusion matrix in which we classify things. So this is a true case, and this is how it was classified. So we can, let's say, detect that we detect signals for almost 90% of cases here. But then the question is, what this detection probability actually means? How we can look at it? So we are looking at the distribution of probability and try to find ways to be able to say that if we say that we put some kind of a false alarm cut at some point, that everything that is on this side of this line is really a signal, right? So that we have some confidence in it. So this is actually quite an interesting exercise for me, because we are of course working to produce a working algorithm, but it's combined with a lot of experiments when we are trying a lot of things and learning things. So for example, how data has to be prepared, what are the loss functions that can be used, and what are better training functions that this loss function is optimized during the training. So we are trying to extremize some kind of a function, maybe a better choice or a different choice. This is a choice actually, and how the training set has to be chosen. And maybe one can have several smaller networks that are doing partially some things, and then from this smaller set of networks, neural networks, classifiers, one can produce a final classification. This is called ensemble learning. So it's a kind of a story that is basically a story of all kinds of mistakes, but extremely interesting, and yeah, this is really good for learning. So at some point we will be done with this, and we produce a nice, reliable classifier. Okay, so that was about classification. So let me have a look. Oh my God, I'm very slow. So let me now talk about a different type of architecture, which is called autoencoder, which basically takes an input and does something with it, and then it produces the output that has to be the same as the input. So this is an identity function. And one can ask the question, why to have something like that? This is completely silly, right? Like why to produce a complicated algorithm that takes the input and produces the input, right? Because the output has to be as close as the input in this autoencoder. It encodes itself, encodes and decodes. So this by itself is not very productive, but what is important is that it reduces the data. It produces some sort of representation inside, in the middle of this process. This is this bottleneck or latent space representation that is very much reduced version of this. And from this, one can regenerate the original, which is useful for all kinds of reasons. One can go further and then analyze this latent space. In the latent space, there's some sort of a probability distribution. The cases or the classes that we, for example, let's treat it as a classifier. We can encode in this variable latent space, which is much smaller than the original. Those parameters that are important to regenerate the classes. So it's like that we have for example, a picture of a number 3. It is being reduced and then it's being inflated again, and this 3 is being regenerated from this latent representation. So this is perfect data reduction. And then next step would be to teach the network, to train it using some conditions. Like, for example, this is a number 3. So it, let's say, has one parameter, 3, the number, right? Parameter 3, right? So we can condition the training with parameters. And of course, obviously, for us, we have waveforms that are composed of many parameters, and we can encode and decode waveforms, and also train the network with the parameters of the waveform. So that would be parameter estimation. This part, the one that is decoding from the probability distribution, we would get estimation of parameters with some sort of estimation of errors, some sort of error distribution as well. So, and this is also being done by our colleagues, this time from Glasgow. And they did exactly this. They took this conditional variational autoencoder, they trained it with a bunch of waveforms, and they at the end requested the posterior distribution from this in the Bayesian inference language. That would be a posterior distribution from the Bayes theorem, and they have compared with the classical algorithm, and they got, in a limited case for a couple of parameters, quite a nice agreement. So they get the posterior distributions of parameters with errors that is compatible with the typical classical Bayesian inference method, Markov chain Monte Carlo. But the good point about it is it's extremely fast. It's like 1 million times faster than the normal method. So this actually opens a lot of possibilities if this is done correctly, because of course, again, this knows only about this training data that on which it was trained. So on a slightly different one, maybe it will not work. So one has to be careful with this. But this is very promising. Then we can think about detecting gravitational waves, not by looking for the waveform, but in some kind of from a different point of view. Like we teach the network, our algorithm, only the noise. We want the network to understand what noise is. And then the gravitational waves would be an anomaly in the noise. So we teach the autoencoder to reconstruct the noise, and then we subtract the output from the input. And if something is left, that is in the piece of data, there is something in addition to noise, then we will see it as an anomaly. So this is produced here by Filip Morawski, Elena Kłoko, Luigia Petre, and me. We have just finished this work. That one can detect the signals quite efficiently. So this is a signal, this blue thing, and then this is the anomaly that is detected. And one can distinguish anomaly distribution from the noise distribution and detect even weak signals. So this is some kind of a measure of how well the anomaly is being recovered from the data. even weak signals can be detected for signal to noise below 10 or something like this. So it's just quite interesting from this point of view. This is a kind of a simple method of doing things, but it works. So we tried this, for example, on the real data, so we can very easily detect signals like this one, 170814 as an anomaly. Can detect 150914, which is very strong. So you can even see some sort of a structure here, and so on and so on. So this is very nice. And another additional point is that it very nicely localizes the signal in time. So we can have some sort of time localization of the signal, which may be important for multi-messenger, because we can have an information about the triangulation, for example, if you have it very fast on many detectors. One can do the other way around, that is remove the noise. So this is called denoising, and one uses the so-called denoising autoencoders. So we input the noisy time series, and we request clean without noise time series at the output. So this is a kind of a noisy time series here. Original waveform is here. The noise is red here on top of, no, sorry, it's not on top of the original. Original is in yellow. But here it's original and the noise almost the same. This is quite a strong signal, so it has to work well. This is a 150914 signal that is also cleaned from noise, and we also provide some sort of estimate for the error of this denoising here. And again, this works relatively well. This is not the final result, but it works relatively well even for not very strong signals. So this is a kind of a metric called overlap, how well this original waveform matches with the noised one. So if it's fast enough, then we can do it in like online, denoise everything, and sometimes we'll find something like that, and that would be the next step for another stage of a pipeline to analyze this further, whether this has desired features of a signal or something else. And this can be also done for basically cleaning the whole data. So we can denoise the data. We can remove these ugly things that come from because of all kinds of reasons, and in this way improve the sensitivity. So there is a very nice pipeline called Deep Clean. They really remove a lot of noise that can be understood by the network. Okay, so I wanted to now talk about something a little bit different, and that this is about using a neural network as a kind of a way of approximating things. So as you know, we have neutron stars that are composed of very dense matter. This is the so-called equation of state of dense matter. We don't know exactly how it is, but we can take the equation of state as an input and solve the Tolman-Oppenheimer-Volkoff equation to get so this is a hydrostatic equilibrium equation to get the mass and radius of a star composed of this equation of state. So what I will show you here is to try to approximate this this set of equations by a neural network. So one can train the neural network to understand the connection between the input, that is the equation of state, with the output, that is the series of masses and radii that produce this lines, right? That all the theoretical physicists from the neutron star community are looking at them all the time because they want to know what is the mass at the given radius, because this is very important. So one usually solves this set of equations, but one can treat the neural network as an equation, kind of a set of equations, and teach the neural network that if you get this input, then you will get this output, or even the other way around. You have set of mass radius measurements with errors even, and you have to recover the equation of state, which is even more non-trivial in this case, because we want to know the equation of state finally, not only the masses and radii. So this is a work that was recently finished by Philip, so we start with something like that. We have a set of measurements, of course, simulated measurements of masses and radii from a specific training data that is basically synthetic data, synthetic equations of state of some sort of piecewise polytropes here. We train the network on this, on the data from those lines, but with errors. So they don't exactly correspond to this red line because there are errors that are selected from a distribution with the sigma corresponding to the error. So they are supposed to kind of simulate the real observations. And after the training, we can recover the equation of state. So this is the pressure versus density relation for equations of state that were not in the training set. So they were the realistic, so-called realistic equations of state, not the piecewise polytropes, but some kind of equations of state that are produced by other people. By chance, they are somehow in this region of space, parameter space, that are corresponding with our training data, and one can recover the equations, which is quite nice. And so one can do this kind of things as well. One can also analyze the distribution that comes from the population of measurements. So imagine that in the future we will have a lot of measurements of masses and radii, masses and tidal deformabilities of neutron star binaries, and we would like to know, for example, what does it tell us about a possible phase transition. So this is some sort of a process that happens on very dense matter, that maybe is a sign of some sort of an exotic phase, quark phase, or some kind of, I don't know, something else, crystalline phase in a very dense matter that is completely inaccessible to terrestrial experiments. So we have so the setup is like that we have some kind of an equation of state. So this is a very specific equation of state that gives this mass radius sequence. So this is it has one branch, and it has another branch on this side that is a quark core star, and we can have a look at the chirp mass and chirp radius distribution. If we assume that we have some random masses of the binaries, then we have a distribution of chirp mass, and also we have corresponding distribution of tidal deformabilities. Of course, this is completely artificial, selected from the uniform distribution. This is another question: what the actual mass function for neutron star is. It's a very deep question, and it may influence the results. But then we have this like I don't know, 50 measurement points, let's say 50, in this plane, and we can apply an algorithm to detect whether this data somehow clusterizes or not. And in this case, we are expecting 3 completely different clusters of data points like that. So this is a very simple case to just show you that one can use algorithms to find clusters or some kind of patterns in the data. On this extreme example, of course, probably the equation of state that gives us the mass radius diagram will be different than this one, but we don't know, and we will have to adjust our methods. But this is a kind of a way to do these things with the population, try to detect physical parameters from the measurements with errors. And the last thing I wanted to say, I'm finishing this, so this is my last slide, is that we can predict, we can try to teach our machine, our algorithm, to predict the future. So for example, we have waveforms that are generated by general relativity. This is a part that we feed to the network, and then it has to predict the end. So again, this is quite important from multi-messenger point of view, because we'd like to know what will happen in the future, because we can, I don't know, point our telescopes there or something like that. So this involves a slightly different type of neural network. This is called long short-term memory network, or recurrent neural networks, that are very complicated small systems that that basically are like time sliding windows on the time series, and they remember a little bit of the past. They can analyze what they saw in the past and give predictions for the future. So this is quite an interesting development recently with colleagues from AstroCent. And at the end, we would like to have this working with the very noisy data and be able to predict, for example, when the merger will happen. That would be quite interesting. Okay, so I spoke for too long, so this is my end slide, just to show you that the field is quite broad. If you are interested in multi-messenger applications of machine learning in gravitational wave astronomy, you can always join this construction. And you're welcome to join. And this review that I was mentioning is this one. So if you are interested, you can read this. Is much more information in the review. Okay, thank you.
Okay, thank you, Michał, very much for this very interesting talk. I'll do the clapping on behalf of everyone. And I think so no one dared to interrupt you.
Why not?
Why not? But maybe there are some questions now. Please raise your hand in the Zoom menu if you want to ask something. There are two questions. Josiah, I hope I pronounced.
Thank you. Yes, that's correct. With some of the denoising or signal cleaning approaches, how did you predict the noise? Did you use any external data, like from a seismic record or microphones or anything of that sort?
So I was not doing this myself, but I know that there is a group working on this exactly. That they are taking all kinds of auxiliary data, microphones, seismometers, and everything, in addition to the main channel, and they do this correlation thing. But the main point is that you can take, if you have enough data, let's say real data from the detector, you can train the network the quality of the noise. So it will understand how the noise process, and then you can ask for removal of this, and only this that will be not the thing that it learned will stay. So yeah, so there are many techniques. So maybe we can talk about that offline, because there are many ways of doing this.
Thank you. Yeah, I'd be interested in that.
One more question from Nada.
Hi, thank you for the talk. I have a question which is more regarding to the first part. I was just wondering, those glitches, Zoo, that you were mentioning in the beginning, are all those real astrophysical events, or?
No, not at all. All of them are not real. That's
okay.
the thing.
Okay.
So we call them glitches, and of course I forgot to say that usually astrophysicists are talking about glitches in case of pulsar glitches, and these are just glitches in the data. So they are basically transient artifacts, transient noises that are of different origin. So, and for us, they are a pest. We don't want them.
Okay. So it's possible that some of them are actually have astrophysical origin, and some of them are just noise, or do I understand correctly?
So I think when we talk about glitches, then we talk about this instrumental glitches.
Oh, okay.
If something will look like a glitch, not like for example, like a binary system waveform, it may be a signal. It may be that there are signals, astrophysical signals, that are looking exactly like glitches, but for this, then we are really in a kind of more difficult situation, in the sense that we don't know the waveform of it, right? So we need to have several detectors working at the same time, and then if many detectors detect the same kind of signal, then we can be more confident that this is an astrophysical signal, because they are really distant from each other. So there is no influence between there is no influence directly on this detector except the astrophysical signal. But one has to also calculate the false alarm rate for this, because by chance they may happen, the glitches may happen at the same time, maybe, and so on and so on. So there's a bunch of statistical tools to do it. But of course, we expect something like that. Like, for example, supernova explosion could be a distant supernova explosion that we will miss electromagnetically for reason. For example, it's on the other side of the bulge, for example. Would be glitchy, would be something like a little burst. And for one detector, we can miss it, for example.
Okay. Okay. Thank you.
Yes, so I think this is even more exciting than those now boring binary black holes, because everybody knows how to find them. Nobody's excited anymore. Joking, of course. But
I have a final question. The boring black holes, we are already bored with them.
Yeah,
so probably you can use your network to predict how many of such common systems signals we will see in 04. In next 10 years, how many?
It depends. It depends on the sensitivity of 04, which is not yet decided. And then there are all kinds of problems with the future. It's difficult to predict the future because it's like with the stock market, because things may happen. Like, for example, there was a problem, something was faulty in one of the detectors. You cannot predict this, or you can with some probability. But it's difficult to predict unpredictable things.
That's the problem with those predictors.
Yeah,
so can you predict the number of COVID cases tomorrow?
Yeah, I think people are doing this because I saw I didn't mention this, but this is a very nice way of a very nice area of machine learning. This is so-called physically inspired neural networks, when you basically can plug part of differential equation into the network, and you can predict a process, like, for example, Lotka-Volterra equations, extremely well. So this is like prediction of COVID cases. I think is also the case for this, but probably one can do it in a simpler way.
Okay.
Unfortunately, I think my prediction is that it will be growing. So
it will be growing. Okay, we'll see tomorrow. Okay. Thank you very much, Michał. Thanks everyone for joining.
Thanks everybody.
And I'll see you next week on our next seminar. It will be the last seminar in the series of gravitational waves. So